This is section 3.4, measures of position and outliers. Measures of relative standing. Relative standing to positions of values within the data. We can apply comparisons of positions to data with different means or standard deviations. For example, would you rather be a big fish in a small pond or a little fish in a big pond? If you are the same fish, does it really matter? I finished 226th in one race this summer and 741st in another. Not for real. Which race did I do better in? Is it far from your seat to the door? The library? The moon? The edge of the universe? That's what we're talking about relative standing. It really just depends on how you're looking at the picture and what you're trying to measure. One way to do this is with z-scores. Measures how many standard deviations a value is from the mean. We can use standard deviations to deviate from the mean, but if we're talking about two different things that aren't really related, then you can't compare their percentiles within the standard deviations because it's on two different levels. So if we put it to z-scores, this tells us how many standard deviations it is from the mean, which then puts everything on the same playing field. So to calculate the z-score, it's simply a formula. This one is for sample. This one is for population. The only difference is the notations. Notice the mean is x bar and the mean here is mu. And one has S for standard deviation and the other is a population standard deviation. So there's really not much difference in them. You take the score and you subtract the mean and you divide by the standard deviation. With the empirical rule, like we said, we've done this. Your standard deviations, you break it down within your percentiles, and your z-score goes right underneath that. And like we said, beyond two standard deviations, we consider unusual values. Same thing with z-scores. An unusual value would be beyond the 2 or negative 2. Our usual range of values spread between negative 2 and 2. So percentiles, deciles, and quartiles, all they are names to break up things into equal sections. Percentiles we know is 100 because there's 100%, and we talk about percentiles according to that. Deciles means you break it up into 10 sections. Deci is 10. So if we say D3, we're talking about 3 deciles, which would actually be 30 percentiles. Quartiles, quarts is 4, so we break it into 4 sections. If we were talking about quartile 3, then that would be like 75% because that would, if we broke percents up into 4 sections, 3 of them would be 75%. So P35 would be 35% and 65%. So 35% better than P35 would be a value better than 35% of the scores. P57 would be a value better than 57% of the scores. Top 10% or would be percentile 90, and so better than 90% of the scores. Or we could say D9 for 9 deciles. Finding a percentile of a score, you take the number of scores less than the X and divide it by the sample. Use the data set to find the percentile of a 10. So a 10 is better than 7 out of 17. So 1, 2, 3, 4, 5, 6, 7. So 10 is better than 7 out of a total of 17 of them, which is the percentile 0.411 or 41%. So we could write that as P41. Use the data set to find the percentile of 17. So 17 is here. If we count, there's 12 here. So 12 out of 17 scores. So 0.706 or P70. Sorry about that. Went flying through the air. Hope nobody got hurt in the process. All my wires. That got it. How to find the value in a data set that represents a requested percentile. So if it's asking for P70, that score is that 70 is better than 70% of the values in the data. So 0.70 number of scores, you would just take 70% times n. And that would be the position 70. Now we have to count to find what value is in that position. So 70% and 30% is what P70 stands for. And 0.7 out of 17 is 11.9. So that would be the 12th score. Which would be 16. So P70 equals 16. And that's saying that 70% of the scores, that 16 is better than 70% of the scores. Okay, I'm going to shut the video off and then start a new video with the notes from 3.4, the example.